Welcome back. We're finally diving into the t-test. This video is all about understanding the real t-test and how it works. Get ready to tackle the t-test together. Okay, let's get started with the t-test. To really understand it, we need to grasp the t-value and the t-distribution. Think back to the z-test. Remember that for a z-test, we needed the t-value and the standard normal distribution. Well, for the t-test, we need the t-value and the t-distribution. And remember, the whole point of the t-test is to compare means, especially when we don't know the population standard deviation. The TF you see here stands for degrees of freedom. Let's delve into what the t-value actually means. Our main goal is to figure out if the average values of two groups are the same or different. We set up a statistical hypothesis to test if the difference between the means of these two groups is equal to 0 or not. The difference we're interested in is in the numerator of the t-value formula. Here's where the statistical thinking comes in. How big does that difference have to be for us to consider it significant? We need something to compare it to. To put it simply, if the difference between the means of two groups is smaller than what we'd expect from just random variation, as measured by the standard deviation, we consider that difference to be due to chance. Now, if the sample size gets larger, the t-value also tends to increase. And furthermore, as the sample size increases, the t-distribution starts to look more and more like the standard normal distribution. In a t-test, the degrees of freedom are calculated as in -1, wherein is the sample size. So a larger sample size means larger degrees of freedom. This larger degree of freedom means we are less constrained by the t-distribution and are more free to use standard normal distribution approximations. Let's look at a practical example. Imagine we're comparing the heights of students from two different universities. Suppose we find that the average height difference between the two groups is 1.4 centimeters. Also, suppose that the standard deviation is 7.05 centimeters and the sample size is 101 students from each university. We can use this data to calculate a t-statistic. After calculating the t-statistic, we need to compare it to a critical value. The critical value depends on our chosen significance level alpha and the degrees of freedom. Let's say our alpha is 0.05, which is a common choice, and our degrees of freedom are 100. Looking up the t-table, we find the critical values to be approximately 1.984 and negative 1.984. These values define the boundaries of our rejection region, representing the extreme 5% of the t-distribution. Now, here's the crucial part. If our calculated t-value falls outside the range defined by the critical values, which is either above 1.984 or below negative 1.984, we reject the nullity hypothesis. In other words, we conclude that the difference between the means of the two groups is statistically significant. If our t-value falls within this range, we fail to reject the null hypothesis, meaning there isn't enough evidence to say that the means are different. So, if we reject the null hypothesis, like in our example, we can conclude that the heights of students at the two universities are statistically significantly different. This means that the 1.4 centimeter average height difference is unlikely to have occurred by chance alone, specifically with a probability less than 5%. While this suggests there might be a real difference in height between the student populations, it doesn't tell us why that difference exists. Further investigation would be needed to determine the cause.